Yes, Vijay, you have some doubts?
No, sir, not doubt. But while doing this course, if there is at all any doubt, we can share with the colleagues. Na?
Yes, yes. I have formed a WhatsApp group. I think you have not got the link, right?
No, no, sir. Please give me the link, sir.
I have just shared in the chat section. I will share again. Okay. So
Okay,
I
okay. Thank you, sir. Thank
just
you.
join the group, and also I have shared the previous week recording of the doubt clearing live interactive session. We already had one week lecture. So I
Yes,
think you
yes.
have.
I have got the emails regarding that.
Mhm. So you
Thank you,
please
sir.
check the chat section. I have provided the links.
Okay, okay. Thank you.
So we'll wait for 5 minutes, I think, then we'll start. Okay, let the people join. In the meantime, if you have any doubt, you can ask, right? So is my voice audible?
Yes, sir, audible, sir.
Yes. So kindly wait for 1 to 2 minutes. We'll start. Okay. Let the people join. So I think we should start, right?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So good afternoon, everyone. I am Subhadip Chakraborty, and I will be your TA for this session. This session is actually designed for live interaction. So I will be planning some problems through which I will make you also learn the concepts, and it will be a practice for the upcoming weeks also. So if you guys find any doubts while solving the problems also in between, you can actually let me know. I have formed a group for that, WhatsApp group. I think most of you have got the link. I will also share the link again. So if you find some doubts while solving the problems, most of the problems will be solving here only. But still, while practicing, if you find any doubts, you can, for that you can join this WhatsApp group. And this live interactive session will be held every Sundays from 5 to 7 in the same link, right?
Yes, sir. Yes, sir.
So how many of you have already uh, that is solved some numericals, and so you can just share your experiences. So if you are finding some difficulties or in solving some particular types of problems, before moving on to the set of problems, if you have any particular problem, if you are facing doubts, you can just share, or then I will move directly into the problems. Yes, you can just unmute
Hi.
and yes.
Yeah, yes, sir.
Hello.
What issue I faced is I actually wanted to have some reference book with which I could refer and then start doing, at least for the quiz one and all. The questions which were asked, I felt were different or were not there in the lectures. So,
Okay,
if there
so
are any,
you can, yes, you can just see the week one live interactive session that I have conducted the previous week. I have
okay,
also shared the video link with you.
okay,
So these
okay,
these sessions are actually designed to make you learn the concepts and such that you can very easily solve the assignment problems. Week one,
okay,
I have
okay,
shared
okay,
the,
fine.
and other than that, I am also solving a set of numericals for
Okay,
which you will find helpful while solving the assignment problems. So you can see the recordings. For week one recording, I
okay,
have also shared in the chat, so you can watch the.
okay, sir.
And for
Thank you.
that, and for reference book, you can follow Professor Bhim Singh's Power Quality book. I will just share the link. I think the book.
Because on Amazon, I checked that book was pretty costly. So
So I
I
think
don't know
you
whether it
mailed
is.
also, right?
Sorry?
I you mailed in the
No, no,
group.
no,
Okay,
I had not made.
okay, okay. Uh-huh. So actually, this book is having copyright, so you can
Hmm.
just see this book, but it is not required because all the slides are already provided in the lectures, and other than
Okay,
that, the example problems I will be solving, so you will not find any difficulty.
okay, fine. Thank you, sir.
Okay, so I will be starting the session, right? So before starting, I think we need some introduction. So is the slide visible? One second. Yes. So I am Subhadip Chakraborty. I am a Prime Minister's Research Scholar in the Department of Electrical Engineering, IIT Delhi, under Professor Bhim Singh and Professor B.K. Panigrai. I did my master's from IIT Delhi and my bachelor's from Kalyani Government Engineering College, and this is my biography. So uh, then I will be coming directly, continuing from the part I left in the previous week. That is the problem solving part. So these type of problems are very common and will be asked both in the assignments as well as in the final exam. So you should have a thorough understanding of the this kind of problems for both three phase and single phase variants, and how to calculate the RMS values, the fundamental RMS values, and all those things. So let's take an example problem. So if you have any doubts while I'm solving, you can always ask, and the previous week's recording I have already shared. So if you watch that, it will be more clear. However, I will be continuing from the fundamentals. There will be no use of formulas as such without letting you know the concepts behind that. So we'll keep it very basic and from scratch. So don't worry, I'll help you understand how those are solved. So just looking at the problem, what it is asked, that it is a three-phase 415 volts 50 hertz 4-wire distribution system, and with that three single phase loads are connected between phases and neutral. So what it is asking is so you have some AC source like this, three phase 4-wire AC source, where this is the neutral, this is the phase A, this is the phase B, for example, and this phase C. And you have connected single phase loads. By single phase loads, what do you mean? Please unmute, and any one of you can interact, because these sessions are designed for interaction and you can practice along with me. That will help you solve the assignment problems. So please be interactive.
Single phase load means it is connected between single phase and neutral.
Yes. Every phase you have the live, and then the neutral is going to this fourth wire, right? And between phase A and N you have one load. Phase B and N you have another load, right? Sorry. So between phase B and then N, you have another load, and then between phase C and N, you have another set of loads, right? Now, each of these loads, how they look, they are thyristor, that is single phase loads. How are they? They are single phase thyristor bridge converters with constant current loads. So you can model, actually these are RL loads where the L is very large. That's why we can model it using a current source. And you have your live and neutral going here. For each of the phases, we have drawn like this. So this is, I can say, L and N. For every phase, you have this kind of load connected. So phase A, phase B, and phase C, these three are having connected single phase loads of this nature. So now what it is asking, that this load is drawing at the DC side, they are telling 20 ampere constant DC current. So this is 20 ampere for each of the phases. And this is all obviously single phase thyristor controlled constant current source, and the firing angle is given as 60 degree. So this is asking you to find the AC source RMS current. So AC source RMS current means this current or this current, that is inside the load, how it is looking. So these currents are being asked, either this current or this current or this current, because this is a balanced condition, right? All are symmetrical loads. So how will you find any idea? How will you find the AC source RMS current? What will be the approach? Anyone?
Sir, I source is will be equal to I naught.
Is it? Just rethink.
I source is equal to I naught current.
Yes, but I naught is like this, right? I naught is this current, right?
Yes, sir. Yes.
So I naught is said to be yes, 20 ampere, right?
Yes.
But how does I source look like? This source current, this one. I hope it is visible, or by other color I am showing. this current, right? I source. So is I source equal to I naught? No, right? Because when the positive cycle will come of the sinusoidal supply, because sinusoidal supply is like this, right? For example, I am drawing here. This is the supply voltage, right? So when the positive cycle will come and you will trigger your thyristor sets here, what will happen? These two thyristors, for example, may turn on. Then these two thyristors will bear the load current. So what is the current direction? Opposite, right? Like this. If you, for example, assume the positive cycle to be this. Agreed? Then what is the current direction? Then current will flow through this thyristor and this, then like this. So the direction will be this way, opposite to the direction of IS I have shown. So for this part, the conduction will happen from alpha to 180 plus alpha. And then when the other sets will turn on, then the from 180 plus alpha to another 180 degree, 360 plus alpha. So this is the magnitude of I naught, whatever the magnitude is. But the current will reverse its polarity. This part is understood? So what one friend was saying, I naught RMS is equal to I source RMS. Because I source is toggling between plus to minus. So I source RMS is I naught RMS, correct? But I naught is not equal to IS. That is the instantaneous value of these two currents. The input current and the output current are not same. So agreed? Any doubt?
Yes, sir.
So could you explain why it is toggling? I missed that point. I naught, you said I naught is also toggling.
Yes. Just visualize what is happening, right? You have these thyristors, right? And your live and neutral is between these 2 points, just like a rectifier. It is a control
Yes.
rectifier. So once you encounter the positive cycle, for example, this is the positive cycle. Which two thyristors will turn on? This and this.
Yes.
So the current direction you just assume, just short these wires. These will short because these are open. These are conducting, right?
Closed.
And
Yeah.
these are open. So what will the
Yes.
current direction to conduct this current, to carry this load current? The current direction should be like this and
Yes.
like this.
Yes.
So if this is one direction of the current,
Hmm.
and then when the other cycle will come, the negative cycle of the sign, then what will happen? The impressed voltage will be like this. So
Okay.
these two
Okay.
thyristors will turn on, and then the current direction will reverse. Same current it will bear magnitude wise, but the direction will toggle. So
Okay.
the RMS values of the currents are same. But
Okay. But the other diodes are those are not firing, correct? The other thyristors are not
no,
firing.
I am firing to, because I have to conduct the current. I have to make some
Yes.
arrangement to fire the thyristors. So accordingly, I am
Thyristors. Okay.
firing such that they can
Okay.
carry the load current.
Okay.
So in that fashion, if you see, then the RMS currents are same for the source and the load, which is given as I naught to be 20 amperes. So you must be able to draw the waveforms, and most common is the three phase and single phase. This is a three phase system, but the connected load is a single phase because it is connected from live to neutral, any one of the phase to neutral. So if you can draw this kind of waveforms, like for example, in this case, the single phase waveform, you see that I naught RMS is IS RMS. And what is the nature of the wave? The wave means the waveform of the input current. This is a square wave, right?
Yeah.
But remember one thing, if you have a three phase load, like for example, three phase thyristor based constant current load. So like this. These 2 points are very important. So if it is a three phase type of, and then you have a constant current load, and the three phases are coming from these 3 points, for example, A, B, C. and you have a constant current load, and someone asks you what is the, and it is a symmetric loading. So any one of the phase input side, if they ask you what is the nature of the waveform, it will be quasi-square waveform that I have already discussed in week 1. You can just see there is a 60-degree gap. That is so that's why it is becoming quasi-square. In case of
Okay.
quasi-square waveforms, also you know how to draw the waveforms. Once you are able to draw the waveform, finding out the RMS is very easy. Now you see, you have a square waveform. How you will find the RMS value? You just to find RMS value, you just square, then mean, then root. So here, if it is square, then square and mean and root, it will come on top. Negative also will come on top this. And when square and root, you will find the same. So the amplitude wise, it is 20 ampere only, and his RMS value is also 20 ampere for the overall RMS value. Now what they are asking you to find in the second part, it is asking that if some arrangements are made using some compensators to compensate for the power factor. Now power factor means that the power factor of the input side is compensated by use of some reactive passive elements, some lossless actually reactive passive elements to compensate for the reactive and harmonic components, and then they are asking you to calculate the AC source RMS current of every phase, because it's a balanced kind of scenario. So only power factor is being compensated because input side power factor was previously not unity. So some power compensating devices are used. So how will you find out the RMS current after compensation? When after use of the compensator, the RMS, the power factor of the input side has already become unity, then it is asking you how to find out the RMS current. That is after compensation. So what will be the approach? Anyone? So now what I have done, I have used a compensator and assume that the input power factor has already become unity. What will be your approach to find out the RMS current in that case of the input side? Anyone? Anyone just can unmute and just say the philosophy behind it. How will you find out the RMS current after compensation? What technique you will use? Anyone just say?
Sir, if the power factor is unity, can we assume a pure resistive load in that side?
Correct. So
Is that
correct.
possible?
Exactly. So to the supply, it will appear just as a resistive load. So what technique then we can use to find out the RMS current? We can use power balance technique, right? You don't have to remember any formula. You just use power balance technique. There are formulas, but if you use formulas for every problem, it will be different. So simply use power balance technique. So power balance means P input equal to P output. Now since this is every phase is connected to some single phase loads, so we do per phase power balance. And since you already know the input power factor, which is unity, what will be the per phase power balance of the input? It is just VRMS into IRMS. That is VRMS phase into IRMS. That is the power. Input power, active power actually. So what is the output power? Can anyone tell? For for single phase SCR based loads, the DC side average voltage, anyone knows? DC average voltage of rectifiers. It is 2 Vm by pi, right? It is very common. And if it is controlled, then it is cos alpha. So this will be same for all kind of problems. If you have single phase thyristor based loads, the average DC voltage will be 2 Vm by pi cos alpha. It will not change with any kind of loading or so. And if you have constant current, then V average into I average, we can say VDC into IDC is the DC side power, or we can write VDC, right? I naught is also DC. So this is the I naught is constant, right? 20 amperes. And this is 2 Vm by pi cos alpha. What is Vrms phase? Vrms phase is the per phase, that is RMS voltage. And IRMS is the per phase RMS current. Because it is a star, line and phase currents are same. But cos theta, that is, this is unity, power factor, that is. So that's why we can write like this. And cos alpha, alpha is 60 degrees. And what is Vm? Vm is per phase peak. So what is the per phase peak? We can write it as root 2 times Vrms phase. That is phase RMS into root 2 is the phase peak. So this RMS phase will get cancelled out. I am doing it by red color. And once you have compensated, that is IRMS will be IRMS fundamental, because only for the fundamental component the active power transfer will take place. That is, I have also discussed it in the first week. If voltage has only fundamental, considering supply voltage is purely sinusoidal, which is in this case, in this problem, and that is 50 hertz, and current has third harmonics, that is 150 hertz, and fundamental 50 hertz, and also many other harmonic components, then remember the active power transfer will take place only because of the fundamental voltage and current components. For other components, that is V50 and I150, the active power transfer will be 0. So inherently, when you write IRMS here, after compensation, you are indicating the fundamental RMS component. So IRMS 1 we can write. So by power balance technique, whenever you determine IRMS 1, this is after compensation, because after compensation power factor unity. So using this technique, you can find out the fundamental RMS component. So IRMS 1 is 2 into root 2 by pi into cos alpha into I naught. So this formula automatically comes. You can cross check that, because you know for square waveforms, it is 4 I naught by pi. You remember this formula from inverters also, basic power electronics. For square waveforms, if you find the Fourier series, then the fundamental amplitude peak, this signal peak, this fundamental signal peak, if someone does, then it will be 4 I naught, if I naught is this amplitude and this is minus I naught, then the fundamental component peak amplitude, that is S peak 1, is 4 I naught by pi. What is the RMS? RMS is peak by root 2. So this is 2 root 2 I naught by pi. Now why this cos alpha? Cos alpha comes because it is a controlled case. So you know that if this square wave is shifted by alpha, then we have this cos alpha term, right? So that's why the cos alpha is appearing. So 2 root 2 by pi cos alpha into I naught. This is the fundamental RMS amplitude. So the first part of the answer, what it comes? The RMS, overall RMS value, since it is a square wave, RMS value remains the same. So it is 20 amperes only. However, if someone asks you to find out the RMS fundamental after compensation, that is they are referring to, so what will be the 2 root 2 by pi into cos alpha 60 degrees into 20. So what it is coming, anyone solve and tell? Please solve with me and then let me know the answer, right? What it is coming? Hello?
Sir, 9, sir.
Okay.
9 amps.
So this is 9 amps, right? So in this way, using power balance technique, you can find the fundamental RMS component. All problems, this will be the approach only. Use power balance, find out the fundamental RMS component. And for finding out the overall signal RMS, you have to draw the waveforms. And after practicing problems, you will not have to draw waveforms also. You can just remember what is the nature of the waveform. Just remembering that this is square or this is quasi-square, you can just find out the RMS. For example, if it was quasi-square, how would you have find out the RMS? For example, 120 degree it was square, and then for 60 degree it was no signal was there, and for again 120 degree. For example, tell me how will you find out this RMS? 0, 120 degree, then 60 degree, then 180 degree, right? So 60 degree, no signal value is there, and again 60 degree, no signal value is there, and for 120 degree, 120 degree, for example, some signal is there. So what will be the RMS? How can you calculate the RMS of this kind of signals? Anyone? For example, this amplitude is I0.
Cos alpha minus 60.
No, the RMS value I am telling. Overall signal RMS value. What is RMS? RMS is square the signal, then mean the signal over the symmetric time period, that is the fundamental time period, and then root over it. So what is the actually its implication? Its implication is area under square of that signal. So just square the signal, then the negative part will pop up on top, and you see it is repeating after 180 degrees. Same kind of signal is there. So just find out the area of the under the square of the signal. So what is that? I0 into then 120 degrees divided by 180 degree into 2, I0 square, then multiplied by 120, that interval out of 180, and into 2 because there is another, this lobe, and divided by, since I have multiplied by 2, I will divide by 360 degrees because total time period is 360 degrees. Out of that, these two kind of lobe, two symmetric lobes are coming because it is a quasi-square. And then I am, so first I did square, then I did mean, that is average of that signal, square area average, and then I have done square root. So it is coming 240 by 360 into I0 and root. So what is that? Root 2 by 3 I0. So for a quasi-square with 120 degree interval, it is root 2 by 3 I0. That I have already also covered in the previous video. You just can refer. For recalling, I am just telling. So just like that, you can solve also this problem. So what is this problem telling? 3-phase line voltage, 415 volts, 4-wire distribution system. Again, 3 single-phase loads are connected between phase and neutral. And 40 ampere is the DC current at 30 degree firing angle. The losses in the distribution system they are asking without any kind of compensation. So if there is no compensation, what is the RMS value of the source? Just we have seen in the previous problem. Anyone? Because this is single phase load with constant DC current source, what is the RMS of the input side current? Anyone? So main point to see is 3 single phase loads having single phase thyristor bridge converter, and 40 ampere is the DC current which is constant. So these are all single phase thyristor rectifiers with constant DC current source connected to them at the DC side. And so if the load current is given to you as 40 ampere, what is the RMS of the source per phase, that is? Anyone? We just saw IS RMS equal to I0. Yes. Yes, this is clear. IS RMS equal to I0 RMS, because for single phase thyristor based constant current loads, you have seen that the signal is a square based toggling signal. And for that, source RMS and load RMS are same. So once we find out the RMS, why we are interested in the RMS? Because the losses in the distribution system are being asked. Once you hear the term losses, you just calculate the RMS value of the total signal, current signal, because that will give you the strength of the IRMS, which will actually lead to losses. So loss is what? Loss is active loss only, active power loss. Active power loss is I RMS square into R. So whatever signal is flowing in the lines, the RMS value of that current signal whole square it into R is the total loss in the distribution system. And since this is a 3-phase, so you have 3 such conditions, 3 such phases actually. So 3 times, and these are 4-wire distribution system, right? So since 4 wires are there, so 4 feeders are there. So what will be the total loss, P loss? Anyone? So I can write 3 into IS RMS square plus I neutral square into, can write here also, R feeder. I square R is the loss. So I square of neutral into R is the neutral feeder loss plus 3 phases. They are all symmetric because all phases and neutrals are connected to symmetric single phase thyristor bridge converter based loads. So neutral current in that case, can anyone tell what will it be? If you have connected to all the 3 phases, that is A, B and C, similar kind of load, that is phase loads, live and phase, same kind of loads you have connected. So what will be the neutral current?
Zero.
Yes, neutral current will be 0. So IN goes away. And then you have IS RMS. IS RMS we know is I naught RMS. I naught RMS is given as 40 amperes. So what is 40 amperes square? 3 into 40 square into R feeder. R feeder is 0.5 ohms. Neutral, there is no current. So no loss for that neutral feeder because current is 0. So what is the power loss? Can anyone tell?
$2,400.
2,400. Okay. Now you just rethink once. What will be the neutral current? Anyone wants to contradict? What is the, because it is not I neutral, it is I neutral RMS, right? And what is I neutral? I neutral is IA plus IB plus IC. So what is the shape of the neutral current? This is correct. I source RMS is equal to I naught RMS, which is 3 into 40 square into 0.5, because load current average is given as 40 amperes. Plus, what will I write the neutral current RMS to be? Will it be 0? Because the loads are symmetric and balanced. Anyone wants to say anything? This is an important point, right? So it will not be 0. Just rethink. Why? Although you have similar kind of loading in the 3 phases, I am claiming that neutral current will not be 0. Why is it so? Anyone? So in this kind of problems, don't be misled. Okay. Since you have similar kind of loading, does not necessarily mean that the neutral current will be 0. Why so? Again, come to the waveform, right? So I just told you how will IA look like. Since I naught is DC, how will IA look like? For a single phase thyristor based converter which is having constant current, the IA phase A current will toggle between alpha to 180 plus alpha and then 360 plus alpha. Agreed? For IA. Just please tell me whether you are clear up to this point. Hello?
Yes, sir. It's clear.
Yes, but what will be the B, phase B current? How will it look like? Will it be similar shape? Agreed, similar shape. But there
Yeah,
will
similar
be
phase
but there will
shift.
be a 120-degree phase shift, which is very important. right? So this signal IA will be shifted to the right, considering ABC phase sequence of the supply. So this is A, if this is VA, then you have VB here, VC here. So if you have this kind of phase sequence, then 120 degree shifted to the right, because 120 degree lag will be VB. And this signal will shift by 120 degree. So that is IB. So how it look like when it is shifting by 120 degree? For example, like this. Again IC. IC will again be 120 degree shifted version of the IA, of the IB, sorry. Again from IB, if you shift by 120 degree, you will get IC, because this is 120 degree apart. So once you sum IA plus IB plus IC, it will come with a square shaped current, because you see, this is IA, right? IA is, this is negative. This is also negative. But when you see IC will, the positive lobe will come here. Because if you see the waveform, so I am drawing it in a, I think I have to increase the slide. Okay. Yes, so this is ISA. If this is ISB, and this is ISC, and this is ISN, which is ISA plus ISB plus ISC. Agreed? Because this is the return path for all the phases, right? So IA is like this. So depends on where you are having the zero crossing. For example, I am firing the pulse if here. If the phase sinusoid is like this, and you are firing here, then your conduction will start from this and will continue up to this point and will be like this. So this is 180 degrees conduction. This is alpha plus 180 plus alpha. So B will be 120 degree shifted version. So whatever line is here at alpha will come at 120 plus alpha. I think this part is clear, right? 120 plus alpha it will come. So 120 plus alpha it came. Again 180 degree conduction, and it will come here. And IC will be 120 degree shifted version. So I just write here.
So wouldn't IB be a little to the left side? Would it be to the right side?
Left of depends, that actually IB similar to ISA but 120 degree shifted version. Then from IB, IC is 120 degree shifted version. So main point is, when you sum up ISA plus ISB plus ISC, it will not be zero, because there is shift. If these three signals would have been sinusoidal signals 120 degree apart, then it would have caused zero. It would have been zero. But if you sum up these three kind of currents, since they are flat topped and 120 degree apart, then your sum will not be zero.
Okay.
Their sum will lead to a square signal. So ISN will look like this. Main point is, ISN is not zero in that case. If only it is three phase is sinusoidally displaced 120 degree, that is balanced currents, then only ISA plus ISB ISC will be 0. But in this case it is not so. So you can also see that these two parts, when you sum up and a positive top comes, then a positive top will remain, and again after that negative top will come. You just draw and see that how that three signals will look like. Just draw three square waves 120 degree displaced and then sum them up. You will get this kind of current, square current. So when you see the RMS of the square current, it is not 0, na? So this kind of current will lead to loss because RMS of it is not 0, although average of it is 0. So IN RMS is also equal to 40. That is the main point which I want to make. Because the loss is due to the RMS value, not the average value. Average value of this signal is anyways 0. But RMS value is not 0. So same amplitude, plus 40 and minus 40, the neutral current will also toggle. So net loss, what you are getting? Just see what is the value coming. R feeder is 0.5. So 4 times 40 square into 0.5. Now where this alpha will come will depend on the given value. This may be 30 degree, maybe 60 degree also. So exact waveform you can only draw when you have considered alpha value. Alpha value, if it is 30 degree, then obviously this signal that you are seeing 120 plus alpha means 150 degrees. 150 degree comes before the sign this zero crossing 180 degree. So it is little here. Okay, but if it is 60 degree, then exactly at 180 degree it would have come, right? So it depends on the value of alpha. But if you sum up those three currents, then they will be square currents, like this pulsating currents. So the RMS is 40. So what is the answer that is coming? Just do it.
4,000 watts.
4 into 40 square into 0.5. It is coming 3.2 kilowatt. Everyone getting? This is for part A.
Yes, sir. 3.2. 3.2.
Yes. So just the part A I have designed specially to make you realize that, like the sinusoidal case, if you have linear loads, these are not linear loads, these are non-linear loads, drawing non-linear currents from the supply. So in such cases, even if they are symmetric loads, this problem was designed just to make you realize that the neutral current still is not 0 and it is causing additional loss. So that's why we are improving the power quality as well as providing load balancing, which you have learned in the week 2 also. So this is the main condition, that it is leading to additional losses. These harmonically distorted currents and neutral currents, circulating currents, all are leading to line losses. So we want to minimize these line losses. That's why we are learning power quality. So this much loss is coming, 3.2 kilowatts without any compensation, if you see. Now, if I compensate using a 4-wire shunt compensator and assume that after the compensation your power factor has been unity, that is given in the problem. For per phase, the power factor is already unity. Then can you calculate what is the losses in the distribution system? Again, similar kind that the previous time also we did, that you just do the power balance, per phase power balance, just like the previous problem, and you will see that the current I0, sorry, IS, I can tell, IS RMS1 for A or B or C for all the phases has come out to be 2 root 2 by pi into cos alpha into I0. Just do the power balance of per phase and see. So every phase is consuming some power. So after compensation, what is the amplitude of the current? The RMS value of the fundamental current. It is coming out as, just do cos alpha is 630 degree, I think. So 2 root 2 into sine 60, right? Into I0 value is 40 divided by pi. So what is the current value you are getting? 31 I am getting 0.19. So please do with me, right? It will benefit you. So after compensation for part B, when you do the per phase power balance, then you will see that the current amplitude has reduced to 31.19. Earlier it was 40. Now the RMS fundamental, which is after compensation, it is 31.19. So if you see, then what is the loss in this case? And will neutral current be zero after compensation? Anyone? Hello?
31.19 itself.
Yes. I am asking that, okay, you have compensated and found out 31.19. Now what I am asking, after compensation, will the neutral current be zero or not?
Yes, sir.
Yes, neutral current will be zero, because what is the role of the what is the role of the compensator? The compensator role is to provide the negative sequence and zero sequence currents, which is leading to unbalance between the three, and its main aim is to balance the three phase currents such that their sum becomes zero. So neutral current obviously will be compensated by the shunt compensators. So after compensation, you will not consider the neutral current because it will be zero. Its RMS value will also be zero. So after compensation, 3 times I RMS fundamental square into R feeder. This is the P loss, new. So what is your new loss coming?
1460.
Okay. 3 into 31.19 square into R feeder. 1459, right? Everyone got this? What's? So now you can find out likewise for other problems also. Just remember one thing, without compensation, when you are not using any compensators, your neutral current for nonlinear loads may not be zero in all cases. Just draw the waveform and see. So for this kind of waveform, you don't need to again do, because you have already drawn, and if you have not, then you can draw the waveform displaced by 120 degree, sum them up, you will see that you have got oscillating currents, square shaped currents. And after compensation, since neutral current is compensated, then you can just assume that neutral current RMS value is zero, and the losses will not happen for neutral current. So the losses will also reduce due to the compensation, unity power factor after the compensation. So current value is also reduced, right? 31.19. Earlier it was 40. So these things are very important. And if you are able to do this kind of problem, then week 1 or week 2 problems will not be issue. So now another problem like this I have taken before moving on to the next section. So anyone would like to solve and guide me how to do? Same, single phase thyristor bridge converter, 10 ampere constant DC current. Feeder and neutral conductors resistances are given, and 3 single phase loads, just like the previous problem. So that it is now asking the ratio of the losses, so with and without the compensator. So same approach you will follow, that without compensator. Now we can do a little fast, right? Without compensator, if someone asks you what are the losses, then you know that for single phase thyristor based loads with constant currents, you can assume the source RMS to be same as the load RMS, but they are not same. The source RMS is toggling current and the load RMS is constant current. Load is constant current, so their RMS are same but not their actual values. So you can write that without compensator, your RMS value, that is losses, P loss, you can calculate. RMS current is 10 ampere only source. So 4 into I RMS square into 0.5. So what it is coming? IRMS is given. It is 10. Anyone? $200, right? So loss. This is the loss.
Sir,
Yes.
yes. Sir, why we are putting 4 in front of this? Sir? Previously we put 3.
Yes. No. Previously also we put 3 into IRMS square into 0.5 plus I neutral RMS square into 0.5, right? Now you
Yes,
saw the I neutral RMS, what it is? It is a square like this toggling. When you do the RMS, it is also I naught, right? Same as the supply.
Yes.
Just
Okay.
for that, we can write 4 into IRMS, because IRMS is actually conceptually IRMS of the source and neutral are different. But for this particular case, the neutral value, RMS value is same as that of the supply, because just see the wave shape, it is square current, right? With same
Yes.
plus I naught minus I naught. So when you see the RMS, it is same as the phase RMS. So 4 into IRMS square into all the feeders, that is every feeder are having 0.5 ohm. So 4 into IRMS square into 0.5. That is the loss during uncompensated case for this type of systems. Now you have used shunt compensator to compensate for the neutral current as well as for the power factor. So power factor now unity. So you know, for single phase thyristor based converters with constant current loads, we have already shown that the fundamental RMS, IRMS1, what is the value? 2 root 2 by pi cos alpha into I naught. I naught you value, you know, 10. Cos alpha value is 45 degree, different in this case. Every case it will be different, so it does not matter. This is always valid because we found this out from power balance. So now you just find what is IRMS1 after compensation, what will be the fundamental RMS of all phases. This will be same. So this is coming out as 2 root 2 into cos 45 is 1 by root 2. So root 2 goes out. So 2 by pi into I naught. I naught is 10. So what you are getting? 6.366.
89.
So 337. You are getting this? Check just.
Yeah, got 6.89.
Oh, it's a 6.89. Okay. I just will 2 by pi into 10. No, the 6.36 I am getting. Pi value you just select 3.141. Okay. 2 by pi into I naught. Cos 45 value and root 2 are getting cancelled, right? So it is 2 by pi I naught. So 2 by pi into 10. 20 by pi you do. 20 by pi you do. 6.37, right? This is the current. So now you find out the losses, and what will be the neutral current in this case after compensation? 0. This is clear. So IS RMS square into R into 3, because only 3 phases this current will now exist. So after compensation, loss equal to this. So 3 into 0.5, this is R of feeder, and since the neutral current is 0, for that particular neutral there is no loss. All the other 3 phases they are having losses, and so 3 multiplied by 3 into IRMS of one phase IRMS is 6.37 square. 3 I square into R, what is it coming?
60.85.
Okay, 60.85 watts. Every one of you are getting, right? I just will check. It is correct. So these types of problem you need to tackle first by drawing the waveform. Just check. Don't go by your analysis philosophy that every time ISA plus ISB plus ISC is 0. It is not true. So this matters because you have encountered additional loss in the neutral feeder. So that's why we learned this power quality and to design the compensating tools. So the next thing we will do actually is to design the compensators, which you have already seen in the week 2 content, right? So week 2, what we are talking about is for power factor. Three things we are doing. So for single phase, 3-phase, and for 3-phase 4-wire. These three kind of systems we already have in our systems, power systems. So we want to improve some particular parameters. So what we want, first thing we want is unity power factor. So why we want unity power factor, anyone? Just be interactive. This will benefit you, this session, right?
To avoid the power loss.
Yes, to avoid the line losses. So when you have non-unity power factor, then to transfer the same amount of active power, you require more magnitude of current that I have already discussed in week 1. So this current, this amplitude increases if the power factor is not good. In that, you don't have to incur any losses, but the transmission companies or the distribution companies, they incur losses because I RMS square into R feeder, just you saw in the previous problem. That additional line losses lead to, it is not economic for the power generating companies because you are not paying for the line losses. So they want your power factor to be improved. Even if you are attaching many non-linear loads or distorted loads, they want from their end, if they are sitting at the substation or distribution systems, then if this is the point from where they are injecting the power at this bus, what they want is, if the bus voltage is V, they want their current I to be as much in line as possible to the voltage. So what this will do, this will enable them to throw more power at the point of common coupling, incurring minimum amount of line losses. Because if it was not unity power factor, then the line losses will be more. But they do some arrangements at their end to correct their power factor. So I think you are familiar with the phasor diagrams. Just assume a single phase system for this condition and see if you previously were not having this compensator. For example, you have your load voltage, assume anywhere your load voltage, and you have not used any compensator. Most of the loads are lagging loads, so the current will lag than the voltage. Now you have this impedance of the load which is leading this current to be lagging. Now you just account for the source side impedance, which is IL into RS. So VL into IL plus RS plus J. J will be 90° anti-clockwise, right? So once you do this, your VS will come. So you see that the current is not maintained at unity power factor. So what you do at the load end, you want your load voltage to be in line with your current. So at the load end, what arrangement you can do? Since your current is lagging, you want to compensate for that reactive current. So break it into two parts, active and reactive. And if someone compensates for this part of the current, then it will be unity power factor at the load end. So load voltage and load current are unity in line. So you need a leading current. Who can provide that leading current? A capacitor. So one thing I want you to be clear about is that whenever you have some impedance Z, it is R plus Jx. So for inductive loads, this X value is positive or negative?
Negative.
For inductive loads, this is positive. Why? Because what is X? V by XL. Sorry, V by IL. Inductor currents lag or lead the voltage. It lags the voltage. So minus 90°. When you bring it on top, some value, let us say X1, angle 90°. So plus 1 angle 90° means plus J. So inductor current always lags the voltage if voltage reference frame you consider. And its impedance, that is the reactance, actually we call it, is positive. Complex, this is plus J into X. So it is positive. So this is known as reactance. This is known as resistance. This is known as impedance. For inductive loads, this reactance, what you can tell XL, is plus J omega L. This is plus. And for capacitance, it is minus J by omega C. It is minus. Now, if you reverse it, then y equal to 1 by z. What is y? What is y called, anyone? Admittance.
Admittance.
Yes, yes. So G plus JB. Now, if B, this B, what is this? Susceptance. It is more, right? G also conductance. Now, when you have inductive kind of loading, what will be B? Since B is 1 by, kind of 1 by x, but not actually 1 by x, because y is 1 by z. B is not 1 by x. Please remember. But since it is reverse, then for inductive loading, your B will be negative. B is negative. And what will be B? B will be 1 by omega L. And so BL. And what will be BC? Omega C. But with a plus sign. And this will be with a minus sign. Minus J by omega L. So this is BL. Right. So BL is negative, right? Minus J by omega L. So anyone having doubt here? So both types you can do. Either you have modified the load and power factor, but someone wants to also improve the source and power factor, that is at the substation. So they will have to push more reactive power using some compensators, and then this current will meet the reactive drop of this impedance. So more reactive power you need, and then you can correct the power factor at the substation. That is the source power, source voltage, bus voltage, that is, and current are in line. So similarly, they have shown, and this can be found out by power factor. While we solve the problem, we will see it is very easy. So now you see, you have already seen in the week 2 that we have done zero voltage regulation. So why we need zero voltage regulation? Anyone?
To avoid undervoltage conditions in the load.
Yes, because under voltage will, the load when it experiences under voltage will draw more current, because load will anyway, because if it is a constant power kind of load, it will draw more current. And if it is leading to, it may also cause over voltage issues. Not only over under voltage, but over voltage issues may also be there during lightly loaded conditions. So voltage regulation is a very important parameter. Mostly at the, I think, distribution side, it is more of a problem rather than the power generator side. In the distribution side, it is a more problem, the voltage regulation, because the load current is changing quite abruptly. So when you see you have a bus at the distribution side, some voltage is there, the line has some impedance, and then you are feeding your loads, right? Here. So if this current at the distribution side is changing quite abruptly, so this voltage across the loads that you are actually experiencing is quite variable. From the daytime to the night time, if you see, even in our houses, the voltage that is coming is quite varying. So these may lead to some damage of our equipments. If there is quite, in the remote areas, it is quite common. So some compensating arrangements can be provided, which will ensure that the amplitude of the voltage is quite, if you draw more lagging currents, your voltage will dip. It is more common phenomena. So to boost the voltage, some reactive currents may be injected, and that will lead to regulation of the voltage. So in that condition, you can find by phasor diagram, just you need to analyze the phasor diagram, that you have a load current which is lagging in nature, which is the most common scenario, that you have lagging loads, and then you draw the phasor diagram, and you see, you will find some Vs, because VL reference, then IL is lagging. Then once you draw the phasor diagram, that is RSIS plus JISXS, and then you find the load voltage, source and voltage is Vs. So Vs, you see, if you want to make it equal to VL, then what is VL? VL is this is VL, okay, this voltage. So you can, from a source perspective, what you can do, you can divide voltage by total impedance. What is total impedance? Rs plus jxs plus 1 by conductance of this total loading, including the compensator. So 1 by YL plus JBC. So YL is the load, that, and plus JBC. So you know na, that if two loads having conductances Y1 and Y2 are connected in parallel, then they are added. And if two loads having impedance Z1 and Z2 are connected in series, then they are also added. So in parallel, since it is easy to sum up the conductances, then you have followed conductance format. And then 1 by conductance is impedance. So net impedance we have got. Then V by net impedance is current. This current IS we have got. Then IS multiplied by other branch. So you have found out the VL. Because current into other branch, current division rule, you have found out the voltage. Then what is the then we have found out the voltage, and if you equate that voltage with the source voltage, with the load voltage, I think VL, if you equate this with this, then you can find that for what value of B, this BC, your actually this equation will hold true, because this equation is giving the condition for the zero voltage regulation, because you have drawn a circle kind of thing to make them equal. So you have mathematical form of Vs. If you want Vs to be equal to VL, what will be the value of BCV? This VCV. So BCV you want to find. Now, if you put it in this equation and equate, then this value will be coming. XS, which is the source reactance, plus minus whole root over x square minus A 2 RS GL plus A GL square. GL is nothing but the load conductance, and by A. So A is RS square plus X square. So this is the source impedance square. Now this is total reactance. From this, you can just eliminate the load susceptance and calculate the value. If it is coming negative, if this value, can someone say, if this value, this compensator, this value, this susceptance value B is coming negative, what can I assume? What it is used there? Can someone say? What will happen if this B value is coming negative? Anyone? Anyone can answer. Hello.
It's a reactor in the.
Yes, yeah, I am telling, if this compensator susceptance value is coming negative, then what kind of element it is implying to? Is it an inductor or a capacitor?
Inductor.
Yes. So if it is an inductor and we are using an inductor to make the voltage regulation possible, zero voltage regulation possible, then you have to analyze that inductor pulls down the voltages. Then must be earlier the load was leading in nature. And if in this condition you need to use zero voltage regulation, you will surely find out B to be positive, which implies that earlier it was lagging, and now you want to elevate the voltage. To elevate the voltage, you need to use capacitor, for which your B value, that is susceptance value of the compensator, will come out to be positive. Agreed, na? So these small implications you need to understand in the exam, which will help you in solving the problems. Not only the memorizing the, obviously formula you need to memorize this part, because the derivation is quite long. So this formula is important, but some additional, some implications you need to understand, that by phasor diagram this will pull down the voltage, the connecting an inductive load and connecting a capacitive load will increase the voltage level. So these small things you need to know. So now moving on to the three-phase, three-wire system. So what do we want? We want power factor regulation. But power factor regulation and zero voltage regulation at the source side is not possible simultaneously. Hope you understand that. Because once you are pushing more reactive power to correct the voltages, then maintaining unity power factor is not possible. Hope it is clear. So power factor, either you want to regulate at the source end or voltage regulation. Either of the two is possible, but not both simultaneously. And another thing is load balancing. You want to balance the connected loads. that such that the effective loading on all the three phases are same. Why is this important? Load balancing. Anyone?
To avoid stresses on any particular phases of the equipment.
Yes. If your load, I think maybe, for example, analyze that three phases you have. One phase you have connected load, other two phases you have not connected any loads. Then it may lead to some, what you can say, that overloading of one of the phases, not better utilization of all the three phases. So some arrangement can be made connecting some lossless reactive elements, which are called as compensators, passive compensators, in the form of shunt, that can help you divide the current among the three phases. So better utilization of three phases, right? Oh, so in that case, load balancing is important. But one thing, can you tell me that in three-phase, three-wire systems, this is a three-phase, three-wire system. So can the neutral current flow here, even if there is unbalance? For example, IA not equal to IB not equal to IC. This is the meaning of unbalance. Will this lead to neutral current? Can neutral current flow here? Is there any neutral wire?
No.
No. So neutral current is not possible. So I neutral not possible. But will there be negative sequence currents here in three-phase, three-wire? Because this is unbalanced, obviously. IA not equal to IB not equal to IC. If you break it down using Fortesque, that is the symmetrical components, positive sequence, negative sequence, and zero sequence. Will there exist negative sequence? Because these are unbalanced currents.
Yes.
Yes, negative sequence currents will exist even in three-phase, three-wire systems. Can zero sequence currents exist in three-phase, three-wire systems?
No.
Why? Because how the zero sequence current look like? Zero sequence current of phase A, zero sequence current of phase B, zero sequence current of phase C. All are having zero phase displacement between them, whatever be the magnitude. But their amplitudes are same and their phase shifts are zero, even for the zero sequence if you break it down. So this type of systems, these three-phase, three-wire systems, cannot contain zero sequence currents or neutral currents. Please note it. So zero sequence currents and neutral currents are absent in this kind of systems. However, it contains negative sequence currents because there is load unbalance. May be possible in these kind of systems. You may connect some between some two phases, one load, and one phase you may not connect any load. So inherently there exists chances of load unbalance, which may lead to negative sequence components, which needs to be compensated with the help of compensators. So that's why load balancing is still an issue for three-phase, three-wire systems. And the third case is ZVR, zero voltage regulation. So these are also you can do, but note these two are not possible at a time. Either one you can do, because philosophy is to regulate the voltage or priority. Which one is you are giving priority? Because in remote areas, voltage regulation is a more priority rather than power factor, because there are very little loads connected at the remote areas. So voltage regulation is still a challenge, and that's why voltage regulation is more of a concern. So that's why ZVR may be preferred in those areas, and it has a different philosophy. And if you want power factor regulation from a substation perspective, then you can do power factor regulation and design your components. So what will be the value of the components? Sorry, your focus should be on that. What you want to do, whether you want to do power factor regulation, component value will be different. If you want to do load balancing as well as power factor regulation, component value will again be different, because what is your aim will decide what component value you require to put in these shunt compensators across the phases. So for that, what we have done, we have actually calculated what will be the value of these compensators. So these compensators are connected across the phases, as you can see. And then what we do, we take their imaginary parts, because these compensators are lossless elements. So whatever be, either they be inductive or capacitive, but they are not designed to take some or absorb some active power. So obviously these are susceptances, purely susceptive elements. So lossless. So they are designed to compensate for the power factor. So imaginary part we are only taking because we already know these compensators will not contain any conductance part. And then we apply the constraints. So if you see what is the constraint, so line voltage we can write, because if you use delta compensators, then what is the line voltage? VA minus VB. So VA minus VB, you know, 1 minus alpha square into VP. So all these steps I think you have already seen in week 1. Why alpha square? This is VA, this is VB. So just alpha. Alpha means one angle 120 degrees. So when you do this, you will see these voltages. And we are just forming the phasor equations. VAB, VBC, VCA in terms of alpha. And then IAB, IBC, ICA. What will be IAB? Because you know na, I equal to V into G. Now we are doing this calculation for purely resistive loads. So only G part is coming. Why purely resistive? Because we already considered that the power factor has already been compensated by some other compensator. So that's why when you consider the total system, then it is behaving as a resistive load, as one of the friends has already said. So in this derivation, what we want to do is, our main aim is to find out the value of the susceptances to meet the unbalance. Power factor is already compensated, that we can find out easily. Just see what reactive current the load is drawing. That particular current, if you push by some compensators, then it will behave as a resistive element. Then after it is behaving as a resistive element, how to balance the load, that derivation we are doing. So when we are doing this derivation, keep in mind the load is already resistive, purely conductive. That's why only GD is coming. You see here in delta, only GD is coming. So that's why. And when you do the derivation, just go through the derivation. If you have some problem, you can ask me, I can clarify. So one thing I just told you, that for this kind of problems, the compensator positive sequence current will be 0, because compensator is not drawing any active power. And negative sequence current of the load needs to be mitigated by the compensator. That I also told you, for load balancing purpose. So I2 plus I2C, just apply KCL. I2 plus I2C is 0. So just solve this, and once you solve this, you will come up with these values. That for delta, what susceptance values of the compensator you need: BAB, BBC, and BCA. And again, for load balancing application, after you balance, then the effective loading is GD equal to GAB plus GCA plus GBC by 3. So these are easy, and when you see the problem, this will be more clear. So after load balancing and power factor correction, if another aim is to provide the 0 voltage regulation, then you can provide some additional reactive power through this supply current, such that this reactance drop is compensated. And once you compensate this impedance drop, then your voltage, these two voltages magnitudes will be same. However, the power factor will not be unity in that case. So as I told, preference after load balancing and unity power factor correction, if some person wants to also go for 0 voltage regulation, then the unity power factor will not be satisfied. It will be violated, because both at the same time not possible. So the same derivation is provided here. Just few slides before we saw 0 voltage regulation formula. Same formula is applicable here. And you need to remember this, because this sometimes the voltage regulation problems, it is very easy to solve. Just putting the values of the source impedance, and you will find out the component value of the compensator, what you need to put in to make 0 voltage regulation. Now coming to 3-phase 4-wire passive shunt compensators. So just one question I will want to ask here. Compared to the previous system, 3-phase 3-wire, this has slightly changed, that the neutral conductor has also come into the picture for the system. So now again asking you the same question, whether 0 sequence current and neutral current can flow in the lines of the neutral in this type of systems. Anyone?
Yes, sir. Yes.
Yes. Here both the 0 sequence current and neutral current can flow. Apart from that, negative sequence current always will flow, and obviously the power factor can be improved. Power factor improvement, as that is compared to the 3-phase 3-wire system, all features we need to provide. In addition, also we need to provide the zero sequence and neutral current compensation. Because writing neutral current compensation inherently means zero sequence compensation, because you know in power systems we had learned these 3 times of the neutral. So once you break down, you will see both are complementing each other. So either you say zero sequence compensation or neutral current compensation. So this additional feature we need to provide. But what type of compensator can provide it? Neutral current compensation. Who can provide? Can delta type compensators provide or star type compensators provide? Anyone? Yes, because star has already a neutral branch that can be connected to the neutral of the supply. So always remember, for neutral current or zero sequence compensation, you need star kind of compensators. And what will be the delta and star doing together then? So we have divided the roles among the compensators. That star will be doing the power factor correction and neutral current compensation. These are philosophies. If you do like this, then the compensator values will come down. So star will be responsible for zero sequence or neutral current compensation as well as power factor regulation. What will delta do? Anyone? So star, I am telling, neutral current and power factor compensation. So once you put in the star compensator, the neutral current will go to 0, and effectively the source will think that some resistive loads are connected to it. However, it is not still balanced. Resistive load, it is appearing to the source, but not balanced. So what will the delta compensator do? Anyone?
For balancing the system.
Load balancing.
Yes, load balancing. Now, by the term load balancing, don't think neutral current compensation. Both will lead to load balancing, but when I term it as load balancing, neutral current compensation previously already taken care by the star. Load balancing means negative sequence compensation. Load balancing, neutral current already, zero sequence neutral current already compensated by star. Load balancing means negative sequence currents will be compensated by the delta. So this delta branch, this particular branch is having the role to balance the load by compensating for the negative sequence currents. Now, since power factor is already taken care of, it is leading to resistive kind of loads, appearing as resistive loads to the source. So all these 2 sets of compensators, these 6 sets, 1, 2, 3, 4, 5, 6, is providing features of neutral current compensation, power factor compensation, and load balancing. And in addition, if someone wants ZVR, then power factor will not be unity. You already know. Then for ZVR, same formula you just apply and get ZVR values for per phase. Now, same, if you go through the derivation, you will find these values. So these values are very important. Now, these values are derived keeping the philosophy that the star is acting as neutral current and power factor compensator. So star, please remember, star, neutral current and power factor compensator, and delta, what it is doing? Load balancing. That is the negative sequence components. So if this is the philosophy, then the values are like this. What is BACY? For the star compensator, when you see Y, it is for the star. So for the AC, BC and CC, C is for the compensator and Y denotes the star. So A compensator, B compensator and C compensator of the star, for the 3 phases actually, the susceptance values are given by this. So BA, BB and BC, you understand what they mean? GB, GC are load conductances of phase BC and BA is susceptance of the load. So all these are load susceptances and conductances. So from them, if someone gives you that these are the kind of loads that are connected and I want these features, that is neutral current, load balancing and power factor compensation, and I want these features, then give me the compensator values. Then the star and delta sets you need to determine. If they ask you star, only give the star values, and delta, they only give the delta. So remember, these values will be different. All these values will be different because they depend on the type of load. whatever, however much load you put in one phase, the value of the compensator for that phase will be different. So these are dependent on the loads. Please remember. So all the values may be different for all the three different sets. So, but these are lossless. These do not account for any active power absorbed by the compensator. So these two are very important, and understanding that where what type of current will flow. So keep these formulas in mind. And so another set of philosophy is there, that if someone wants to find out that imaginary part of positive sequence component of load current is eliminated, so what it is doing, then if with delta you are mitigating the power factor as well as load balancing. First formula what we saw, that delta was responsible only for load balancing. Now if delta is responsible both for power factor correction and your load balancing, then the formula will be different. So this formula is coming like this, both for the star and the delta. So everything depends on philosophy, with what compensator you want to do what. So more common is this one, this formula. So you remember this formula, and with this most of the problems will get solved. If you are clear with the concepts, so then you can solve most of the problem. So ZVR formula remains the same for per phase, right? You break it down into per phase and put in the values of the load, conductance, and get the value of the compensator for that per phase that is needed for zero voltage regulation. So on a per phase basis, you can actually calculate all the compensator values for zero voltage regulation. Now you come to the set of problems. Now, what it is asking? It is asking that you have a single phase load, simple condition, a single phase load and AC voltage, and it has to be realized using, it has to be compensated actually for unity power factor at the load terminals using some passive shunt lossless elements, L or C. Now that will depend upon what kind of load you have connected. So that will decide actually whether it needs L or C as the compensator. So you try this, how you will do, you tell me. Anyone? Please do with me. All the assignment problems you can solve easily if you try these problems. Yes. Anyone wants to try? It is very easy problem. I can draw the diagram. It is 220 volt, 50 hertz supply, and you have a simple load connected here. So Z is given to you, and you just need to determine what compensator additionally I will put here such that I get unity power factor load. So it should appear to the system that it is unity power factor. So what you will do? Anyone? So what it will do? Apply KCL. IS equal to IC compensator plus IL. If IL has some reactive part, who will compensate it? This one. Such that if your compensator is compensating for the current, that is the reactive currents, then your source current will think that it's a resistive load together sitting here. This net load, that is compensator plus load combination, will act as a resistive load. So your unity power factor will be there. So how will you calculate? So IS, previously when you have not used any compensator, what is IS? 220 by Z, 220 angle 0 I can write by Z. Z is what? 20 plus J15. Can you write it in polar form? Can someone do it and tell me in polar form? Please try. So what it is coming, 20 and J15, right? Everyone is comfortable with polar form? How to bring it to polar form? Nobody is replying. I cannot understand.
No, sir. Sir, could you explain once about how to
Yes,
convert?
yes. Yes. So this is 20. Draw it in a coordinate frame. This is rectangular frame. 20 is in the x and j is 15. So this is 15. So it is in the first quadrant, right? So what kind of I can draw in polar form? So what is the amplitude of this? 20 square plus 15 square. Okay. And then angle, this angle, take always in the anti-clockwise direction. So what is this angle? Tan inverse of, what is this? Y by x. What is y? 15 by 20. Now you can write in degrees for ease of calculation. Can someone do and tell me?
25 angle 36.86.
Correct. Good. Now, since someone was telling that they are not comfortable with the polar representation, I will just give another example such that they will not face the problem. For example, someone tells you 3 minus j4. Which quadrant it will lie in? Who was facing the problem? Please respond. 3 minus j4. First you draw in the plane. How will it look like? 3 j4. J means this is j axis, complex axis, argand plane. And this is 3. So 4 is here. What angle will I take? You always draw like this, the arrow. So the angle you take like this. Because angle will vary from minus pi to pi. So if it is lying in the fourth quadrant, you cannot write it like minus of something. Like this angle you cannot consider. It has to be between minus pi to pi. So we took this angle. Now you just calculate the magnitude of this angle. Tan inverse 4 by 3. So there is a set of rule that 37 and 53 degree. I think you know. Whichever side is having the, this is 5, right? So this is having 37 and this is having 53. 3, 4, 5 triangle everyone knows, na? This is 3, this is 4, and this is 5. Since this is 4, it is 37. Since this is, I think, 90, and this is 3, okay, so this is 53. The smaller side will have it, na? You can remember this. So this was 5, this was 4. This is 4, this length, and this length is 5. So since this is the bigger side, so this is having 53 degrees, and this 37 degrees. Clear?
Yes, sir.
So always answer minus pi to pi in polar form. This is very important while you do these calculations. So tan inverse 4 by 3 was just an example. You can just let it go for the time being and calculate the actual polar value for the signal that we are currently talking about. So once you find out the polar form of the current, because this is important, because we are doing product and division. So always while dealing with product and division, polar form is useful. While doing plus and minus, the Cartesian form is very useful, or the rectangular form, whatever you tell. This we write, na? 20 plus j15, 20 minus j15. These are all rectangular form. And when we convert them into polar form using root over x square plus y square whole root over, that is coming 25, and tan inverse this by this, y by x, by drawing this kind of diagrams, it is in polar form. Why we do this? Because we want to find I. I is v by z. Both are in polar form. So division in polar form is easy. So what is z in polar form? One friend told 25 angle 36.86 degrees. What it is coming? Anyone in polar form?
38.8 angle minus 36.86.
Yes, very good. So if you break this down again into your, it is very easy. If you break it using 8.8 cos minus 36.86 plus 8.8, obviously put a j, sine minus 36.86, right? To break it again into the, just see the projection. If you break this into x and y again. What will it be? X cos theta plus j sin theta, right? Right, like that. So when we do this, then IS what is coming? 8.8 cos 36.86. Always remember 36.86 means your 8. So 0.8, 0.6. You can just remember this pair, 0.8 and 0.6. Whenever do you see this? Cos inverse 36.86 is your, sorry, cos of 36.86 is 0.8 and sine of 36.86 is 0.6. So this pairs you can just remember. So what is coming? 8.8 into 0.8, it is coming as 7.04, and then into 0.6 it is coming minus j 5.28 ampere. Everyone got it? So use geometry in this kind of problems. If you use geometry, then it will be very easy. So everyone got up to this? It is before compensator. This is the current, right? Hello.
Yes, sir.
So before compensator, this is the current. So what is the reactive current? 5.28 amperes. This was being drawn by the load, which was leading to non-unity power factor at the supply end. Now, when you plug in a compensating element, what is the role of that? Only to compensate for this reactive current. So IS new is only the active component 7.04, because the other reactive component is compensated by the compensator. Just remember Kirchhoff's current rule, that this current is this current plus this current. So load current reactive component will be borne by the compensator, such that this current is in line with voltage. So 5.28 ampere, the reactive current, is the compensator current. So if the compensator has to draw 5.2 ampere of purely lagging current, because this is minus j, so it should have injected 5.28 ampere of leading current, such that those two components plus j and minus j will cancel out. So you can write IS new is 7.04, which is asked in the first problem part. So after compensation, IS new is 7.04, which is in line with the voltage, and compensator current, you note 5.28. So if the compensator current is 5.28, can anyone tell me what will be the value of the capacitor? Compensator is, this is not in the problem, but still you calculate. Compensator is drawing 5.28 ampere of current. What will be the value? Leading current. Compensator has to draw leading current, then only these two sum will be 0. So plus j 5.28 ampere it has to draw. So it has to be a capacitor. So what is the value of the capacitor? So V by I is Z. Either you do V by I equal to Z, and Z you put it in as XC. XC is 1 by omega C. So what is the value of C? B omega C equal to I. Right. So what is C? I by V omega. So you put it I 5.28 here. V you put 220, and omega you put 2 pi f into 50, 2 pi into 50, that is 100 pi. So omega is 100 pi, voltage is 220, and current is 5.28. Now how I understood this will be a capacitor? Only if the current is lagging, because lagging currents can be compensated by capacitor. If it is an inductor, then the current would have been leading. Current leading means you have to use inductor to compensate for the leading current. So since this was a lagging current with minus j, I came to know it is a capacitor. So I want to find the value of the capacitor. Using this relation, I find V omega C equal to I, and then I is 5.28 by voltage into omega. Can someone calculate? 5.28 by 220 into 100 pi. This is the capacitor value. Calculate what it is coming in microfarad. Tell me.
764 microfarads.
Yes. No, not 764 micro. It is, I think, coming what by
Sorry, 76.
76 microfarad. So you understood the concept behind it. First, see how is your current of the load without any compensator. That will give you the implication what type of compensator you need to plug it in. If the current is lagging, plug in capacitive compensators. To find out the value of the capacitive compensator, you know capacitive compensator will only take the burden of the reactive component of the load current. Reactive component of the load current you can find from here. Amplitude you know 5.28. Just use that and find out the value of the capacitor. Voltage you know, frequency you know. It will lead you to finding out the value of the capacitor. So use plain geometry, no formula you need. Now equivalent resistance in ohm. One friend told in the starting that once after you use the compensator, the total system acts as a resistance. So can you find out the total resistive load? No. How can you find out easily? No need to find out the parallel of these two components. It will take time. What do you do? V by I. V 220 and I only inline current you take. After compensation, only the inline current 7.04. So 220 by 7.04 is the R. That is the resistance. After compensation, it will act as a resistive load. So V by R you do, you will V by I you do, I inline, and you find out R. What is R? 220 by 7.04. What is coming? 31.25 ohms. So second part answer you find out, right? Clear?
Yes, sir.
Let me move on to the next problem. Same kind of problem, but now it is asking you to calculate the values, the value of the compensator and the kVA rating of the compensator. What will you do? Same. You just use this J. What is Z? Write it in polar form. Now calculate and tell me what is polar form. You do with me. Otherwise, it will be of no help. Yes, hello.
Sir, 14.14 angle 45.
14.14 angle 45. Correct.
Yes, sir.
So everyone understood how we did the polar transformation. You just draw 10 J10. You just sum it up, phasor summations. Then 10 root 2 will come, and this will be 10 inverse 10 by 10, which is 145 degrees. So 10 root 2 is the amplitude of the polar, and then 45 is the phase. So that's how you calculated, right? And you have already calculated the Z in the polar form. Now, what is the value of the current? You have found out, na, Z value. Now, voltage, you know, 220 angle 0. So, what is I? 220 angle 0 by 14.14 angle 45 degrees. What is coming? Tell me in Cartesian form. Take the polar and then do it in Cartesian form. So you know by seeing the impedance, since the impedance is plus, one thing should strike you. It is an inductive kind of load, so current should be lagging. So calculate. Current should have a minus J component. Because impedance is having plus J, it is implying that it has a RL load. So calculate current in Cartesian form. What it is coming? Every time you have to do in Cartesian to find out the reactive component to design the compensator value. So what it is coming? Tell me. What?
Sir, 10.99 angle 10.99. Approximately 11 angle 11.
So 11 angle 11. What it is? 11 minus J11. It is coming. I think.
Yes, sir. Sorry, sir. J minus J. Sir.
Okay, okay. So it is reactive current, right? Lagging current. Minus J is implying, right? So your compensator should be a capacitor to push the leading current such that it can throw the leading current of the inductor and make it appear as a resistive load to the source. So 11 reactive current needs to be pushed by the capacitor. Understood? Coming from here. So what is the capacitor value? Just we saw what is the V. VC equal to I by V omega. Agreed? So what is I? 11 by 220 VRMS, this VRMS, single phase, so 220, 2 pi into 50. What it is coming? Capacitor value, tell me. Yes, please interact. Do with me such that it will be helpful. What it is coming?
159 microfarads. 159
Okay.
microfarads.
Into 100 pi, right? Yes, 159.15 microfarad. Now, if someone asks you what is the kVA rating, what will you tell? kVA rating, part A is solved. kVA rating. What is kVA rating? It is voltage into current drawn by the capacitor. Current is 11, voltage is 220. So V into I, VC into IC you can write is the S compensator. So 220 into 11. So 2.42 kVA. Right? It was easy. So now let's come to the third set of problem. A single phase AC supply has AC mains 220 volt, 50 hertz feeder. Source impedance is 4 ohms. Inductive reactance, which single phase load you have given here. ZL, this is 6 plus J12. Shunt compensator should be used to raise the voltage. That is zero voltage regulation. You just see the key points of the problem. What it is asking. You want to do ZVR for this load where ZL is 16 plus J12. Your aim is to do ZVR, and for that you need to design the compensator. So it is a ZVR problem. So what your ZVR formula? So B ZVR, I can write x of s plus minus xs square minus xs square plus rs square into 2 into rs into gl plus this g, rs square into gl square plus xs square into gl square. Okay, and then you have this divided by your xs square plus rs square. Now why this plus minus? How to decide which one you will take? Anyone? I already told you, just see the impedance. What it is like? ZL is plus J. So what type of impedance it is? RL load, inductive load, right? Or inductive dominated loading. So if the loading is inductive dominated kind of thing, in order to do ZVR, zero voltage regulation, what kind of element you need? Because inductor and the source impedance, whatever it is given, the source impedance is given, 4 ohms. So 4 ohms inductive reactance, that means your source reactance is 4 ohms, that is given, J4, and R of source is nearly 0, that is also given. So all these inductive elements, the load inductance and the source side impedance inductance, all are leading to inductive drops. So the capacitor needs to be deployed to compensate, that is through the reactive power and compensate for these inductive drops. So you need capacitive element here because these are inductive dominated system. In order to do ZVR, you need to first compensate for the load reactive power to bring it to unity power factor, and then again compensate for the source side impedance drop to do it zero voltage regulation. So for that, you need to use capacitive elements. So B susceptance should be negative or positive in this case for capacitors. Plus or minus J. For capacitors, susceptance should be plus J or minus J. Hello.
Plus.
Yes, plus J. So you, when you solve, you take what? Plus sign or minus sign?
Minus sign.
No, how you are telling minus sign?
Capacitive, no, it is we are taking.
No, you want plus J. So
Okay.
solve because capacitor susceptance is plus, right? Not impedance. I am talking about susceptance. Please don't
Yes,
confuse.
yes.
You be very careful while doing these kind of problems. If you take the reverse, then the answer will be wrong, right? So be very careful. First, see the ZL. It is inductive. So for ZVR of inductive dominated loading, you need capacitor. For capacitor to be there, the B should be plus J. So whatever be this total expression value coming, it should be plus J. Accordingly, choose your symbol, right? So you have the values. XS is J4. So XS, this is XS, okay? XS value you have. RS value is 0 because the source side impedance has no reactive part. Sorry, has no resistive part. The reactive part is J4. So you plug it in. And the load conductance GL, how will you determine load conductance? 1 by 16 plus J12. So ZL is 16 plus J12. So YL is 1 by ZL. 1 by 16 plus J12. 1 by 16 plus J12 is coming what? 0.04 plus J 0.03, right? Just check. YL this is. So this is GL and this is B of L. There will be a minus sign, right? This will be a minus because it is inductive. So since it is inductive, the susceptance should be negative. Just check 1 by 16 plus J12. Your conductance, load conductance and susceptance should be 0.03, 0.03. Okay. So once you plug it GL, BL values, GL and BL values all you plug in, and then you see B value will come out. So this B is B total, right? B total. So B total, you know what will come out? B total J 0.0332. From here, B total, you find out C total. What is C total? B by omega. Because what is B? B is omega C. Omega C total, right? So B by omega you do. C total is coming out 105.75 microfarad. Right? Hope this is clear. So now see this problem. So you have to do power factor correction and load balancing, right? So it has already done and designed the compensator. What it is asking you after compensation, you just calculate RMS value. So what it is? Only single phase load is connected to the 3-wire system, 3-phase 3-wire system. So loading is 30,000 watt. Okay. And what is the voltage? Because this loading will now, after load balancing, will be split among A, B, and C. So do power balance. 30,000 is the net power, and it should be split at unity power factor equally among 3 phases. So √3 into VL into IL per phase after balancing. And it is unity power factor since you have done load balancing as well as power factor compensation. So net load is this, which will be split among the 3 phases after compensation at unity power factor, and then you can find out IL value. IL RMS actually. So what is IL RMS? Using power balance, net power balance apply. Okay. What is IL RMS coming? Just calculate 30,000 divided by √3 into 400. What it is coming? 43.301 amperes. This is for per phase basis. Line current. This is star, no? So that's right. Right?
So one doubt. Here it is written as a single phase load of 30 kilowatt. Why are we again dividing it by the 3 per phase?
No, not dividing by 3. We have not divided
No.
by 3. Total load.
Yeah.
What is the total load? When you use
Okay.
compensation, or even you don't use compensation, load will be 30 kilowatts only. No matter whether it is connected among 2 lines or 3 lines or whatever, net loading before and after compensation on the system will be 30 kilowatts. So that is there. What I am doing power balance. So before compensation was the load 30 kilowatts. Now, once you have provided compensation, your power factor has gone to unity for all the 3 phases. And load balancing. Why we do load balancing? I told you, to split the power among the 3 phases equally. So 3-phase power at unity power factor, you know, √3 VLIL into cos phi. Cos phi is 1. Now, what will be the current of all the 3 phases after compensation? That is after balancing the load. Then current we are calculating. But still, the net power, this is 3-phase power, right? √3 into VL into IL.
So why are you saying it is 3-phase? In the question it says it's a single phase
I
load of
understood.
the
Yes.
yeah.
You just understood. You just think it like this way. A single phase load is connected there. However, but hello. Yes. Am I audible? Hello.
Yes, sir, you're audible.
Yes. What I am telling, single phase load is there, but this single phase loading on 2 lines has to be made in such a way by compensation that it comes on 3 lines. This is the meaning of load balancing. Even if load is there, only single phase load is there between 2 lines, for example A and B, you have to provide compensation and do load balancing. That's why we do load balancing, such that loading is borne by 3 lines equally.
Okay.
Single phase load, agreed, but the total loading 30 kilowatt needs to be done in such a manner that it is split among 3 lines. So assuming that you have already designed compensators to compensate for the balancing the loads of 30 kilowatt on the 3 lines, your 3-phase power still remains 30 kilowatts only on the 3 lines also, even if it is a single phase load. For best technique to use here is the power balance. Net 3-phase power and any power, single phase or whatever loading, net loading needs to be same even before and after compensation, because remember, compensators don't draw any active power. Only compensators don't draw any active power. They are only used for mitigating the that is balancing and then power factor correction, all those techniques. So negative sequence components, but they don't themselves draw any reactive power. Themselves don't draw any active power. Sorry. So that's why the single phase loading of 30 kilowatt, in order to provide compensation and make it balanced, after that the current will be 43.301. And even you can cross check that 3 into 43.301 into your 400 volts will come out to be 30,000. 400 by √3. What is your per phase voltage? 400 by √3. Per phase current is this. You do it, you will get that 30,000. Just do it. 3 into 43.301 into 400 by √3. It is coming. Just check. Per phase voltage into line current into 3. So what your compensator has done, it has equally spread out the load, the single phase load of 30 kilowatt among the 3 lines. Load is still single phase, but that loading is spread on the 3 lines, such that it appears to the line or from the source end as a 3-phase balanced system. Only for that we are using it. Okay.
Okay, sir. Understood.
So please don't get confused. This is very simple. That's why we do the compensation and the load balance. That is the whole purpose of the.
आता उघडू नका, कसलं उघडू राहिलं? आता उघडू नका.
Hello. Yes. So next problem. Next problem is also easy, I think. Yes. So just see this problem. This will clear your doubt. Read this problem. Next 2 problems I will do in the next class. 2 problems are remaining still. But okay, up to this it is okay. So this is the last problem for today. You just solve this problem. It will clear your doubt. The previous problem. So how will you do? Anyone? So what it is telling, it is a 3-phase 3-wire system, right? And you have to provide load balancing and power factor correction. Single phase load is connected to any of the 2 lines, of 20 kVA at 0.8 power factor lagging. So net loading is 20 kVA at 0.85 power factor lag. So what is the active power? Whenever they are asking you to calculate AC RMS current after compensation, do power balance. So what is active power? This is the apparent power multiplied by power factor. This is the active power, which is responsible for the load, this power. So what is the, this is the net load active power demand. Net load active power demand will be borne by the three phases after compensation. So just apply √3 into VRMS into IRMS line to line. So this is 415 into your IS. Agreed? So what it is coming? Hello?
$23.
Okay.
23 amps.
23.65 amps.
Yes, yes. So just to see it from another angle, just I will stop after showing you this, that what is actually the current. So can you say me what is the power? 20 into 20,000 into 0.85.
17 kVA.
17,000, right? And what is the current if I assume that it is fully balanced system with unity power factor? What should be the current in that case? So write like this: S into power factor to find out the net active power divided by, this is the power. Now this power is divided among the three phases equally, and you find out the phase voltage to find out the current. So this is phase V phase RMS. So you should find out the same answer. Just check. 17,000 by 3. Okay. Divide 415 by √3. Okay. Around 23.65 it is coming, right? So same power balance technique I have done here. Convinced?
Yes, sir.
Okay. So these are the two perspectives. Any perspective, per phase perspective, you can look it like that. That the philosophy like we used here, that the power factor is now unity. So my active power will be split among the three phases. This is like load balancing concept, where you split the power by 3 and do per phase analysis and determine the current, like we have done here. Or you use complete active power balance for 3-phase net. That will also give you this, because inherently you are assuming that the system is balanced after compensation, right? Okay, so we'll stop here, and two problems were there remaining, so I will continue in the next week. So meanwhile, if you have any doubt, you can message in that group, and I hope all of you have already joined that group, WhatsApp group, because there you can post your doubts, or there is the discussion forum also. You can post your doubts. I will share the WhatsApp group link here. In the chat box I have shared, or else you can send me an email to you join the WhatsApp group, and this is my WhatsApp number. You can contact me for any doubts, and better you can post it in the group so that everyone can see and there have an interaction. So please solve problems. I will be sharing some problems with you, which will actually help you in week 1, 2, and 3 together. I will post some sets and then with some answers, maybe 1 to 2 variants, and then you can solve, right? So, okay.
Sir, please provide a recorded video within 1 or 2 days, because we have to submit assignment on Wednesday, sir.
Okay. No problem. I will provide. But
Thank
it
you,
is
sir.
preferred that you solve with me. I will share the recorded video, no problem. But you please solve with me, okay?
Okay, sir. Okay.
Okay. Thank you.
Thank you, sir. Thanks a lot.